tips. Everybody has their TI out?
What's the TI?
TI 89. Okay.
Yeah, what's that?
That's your stats list editor. And in that stats list editor, you're going to have your proportion Z test. So you're on F6. Okay, you have to have your 89s out. Oh, mine out too, but
Mine
you
says
can't see
titanium
it.
next to it too. Yeah. Is that fine?
Mine is a dash 89.
And, excuse me, I'm not on my stats list editor yet. Apps. It's under apps. Okay. Stats list editor. Yep. And we're going to go to the fifth option, which is F6 tests. And the fifth option is the one proportion Z test. Okay, we're going to be here a lot today. And P naught is your proportion from the null hypothesis. Everybody see where that screen is? And you've got the next two things are the successes X and the number of samples. That's perfect. That is the sample size. You're also given the option at this point to judge your alternative hypothesis. And that's basically based on the wording of the problem. Okay? All right. I think we're ready to try a problem with our wonderful tools now. Here's the male births problem. Study from India reports that in 1993, in one hospital, 56.9% of the 550 live births were boys. That seems kind of high, doesn't it? What would you expect it to be? 50, yeah. It's a fact that male babies are slightly more common than female babies. Oh, okay. The study's author reports a baseline for this region of 51.7% male live births. So how does that change what you might have been thinking of for the null hypothesis? You might have been thinking male, female, 50-50, so we're going to have the null hypothesis be 0.5. Now you're changing your mind, right? What are you thinking for the null hypothesis now? What should the null hypothesis be here? The status quo, 51.7. That's what the authorities, the reports a baseline for the region, 51.7 male live births. Now this still seems high, right? They might say, oh, it's only 5.2% higher, but there's no way to judge this if that's a big gap or a little gap until you've studied the distribution of all the possible sample means.
Do you do P equals 51.7 or 0.517? Or does it not matter?
I usually just, it's easier for me to write the decimal, 0.517.
Okay.
And also you're going to want to do that in your calculator too. You don't want to constantly change your percentage into a decimal, so. Yeah. Okay, we're ready for the next one. First we wonder what the sample proportion of 0.569 indicates. What's our symbol for that? What's the 0.569 going to be? P hat, the sample proportion, right? And it indicates that we're a little higher than normal. Could this be explained just from natural sampling variability, or does the evidence suggest that there really has been a change in the percentage of male births? Okay, so that's just a little discussion before we get on with the topic here. Let's come up with our hypothesis now. What are we going to use for our null hypothesis?
P equals 0.517.
P equals 0.517. Right. And you can state that in context as well. That is, the proportion of male births is 0.517 in this region. Now the alternative, the alternative is going to be an inequality of some kind, right? So don't just give the sample statistic as your alternative, but use the sample statistic and the wording in the problem to judge which way your alternative should be. So let's back up to the wording again to see if there's anything in there. It's a fact, okay, reports that one hospital had 56.9% of 550 live births for boys. So, nothing in here is really, in the verbiage, giving you a direction for what you're trying to prove. But what does the report from this one hospital tend to indicate? It's greater than, okay? So we're going to go with greater than. And you're checking out your correct? Sounds like this last game will be greater than. Okay. So P is greater than 0.5 on this stuff. Notice the sample proportion does not come up in here.
She said not equal to 0.5.
Really?
Yeah.
Because
Oh, I'm just kidding. So it would also be okay to do, well, there's like a little note, so you can do whichever, or do a two-sided test is better, though, she says.
okay, mainly because we should practice looking at a two-sided test too, right?
But because the original question only asked if there was a change, not an increase.
Oh, I'm sorry, did I miss that? Let's look carefully back at the reading again.
Has there really been a change in the percentage?
It's a fact. Oh, okay, I'm sorry, there's more question here.
Yeah, right here.
Oh, right here. Has there really been a change in the percentage of live births? So I'm sorry, I didn't realize this was part of the base of the question. So, let's change our minds on that then. In that other verb, we definitely went with not equal to, and we can also practice doing a two-sided test. Okay, the independence assumption, is this do we have a random sample?
Yes.
Simple random sample?
See, no.
What have you got here? And what are you trying to make a judgment about? What is the population? And this is a reason why usually we like to have the hypothesis written out in words. Which you have in here? In terms of written out in words for the hypothesis. Or does it just have these two symbols? Oh, okay. See, I've seen on the AP a lot, sometimes you can get by with this because you're specifying the correct population parameter with a standard variable for it. So when I read this, I'd say this person knows to talk about population proportion in my analysis. But it's also a good idea because you're eventually going to have to mention in your conclusion too, what's the population you're trying to make a judgment about? Just births at this hospital? In this one region of India? Because it did say back here, that the percentage of male births, it doesn't really say where though. And you've got this historical percentage. So it's like we were doing with that baseball problem again. We really don't have a simple random sample of all the historical births, live births in this section of India. What we've got is the last 500 whatever at this hospital. Now, it might not be a simple random sample, no, but it is representative. Unless you think there's something strange going on. This is quite a few births that they've recorded, maybe over the course of a year. And so I think it's a good indication. Is it, do we have the 10% condition?
Yeah.
Is this less than 10%? How many were there?
550.
550 births. Is that less than 10% of all births? Yes. So we've got those conditions. And the success-failure condition, you can actually look at the number of successes, because doesn't it tell you how many live births there were? You have to be looking back, otherwise I got to have to flop back here, okay? What does it say for, there were the 550 trials, but how many male births were there?
56.9%.
Okay, you're not giving me the success-failure condition. That also has the sample proportion. And when you do this, it's n times p greater than 10, n times q greater than 10. Notice we're going back and using the population proportion. So you can take 0.517 times 550. Because that's the sample proportion. And the sample size assumption is better off done with the NP and NQ. Right? Because we're trying to judge this sample size of n equals 550. Is this big enough? We'll just have to take a second here to align this. Okay. It should restore. There's the thing that says restore. Oops. Oh, here it is. There's our writing. Okay. Our n So we have to take NP is 550 times 0.517, and NQ is 550 times 0.483. And both those are greater than 10. So we're good to go. Since the assumptions and conditions are satisfied, we can model the sampling distribution with a normal model and do a, what's it called? One proportion test. Okay, any questions on that? Okay. Now we put all these things in the model, and also we can use our calculators to really speed along the process here at this point. Okay? What was the P naught?
0.517.
That's from your null hypothesis. You're assuming the null hypothesis, that is P equal 0.517. Q naught then is 0.483. The number, you remember, is 550. Right? P hat is 0.569. And the standard deviation. I'm going to jot down the formulas, and then we'll actually get all the key numbers. I'll show you how to get the key numbers off of your calculator without having to go through a lot of the drudgery of actually doing a square root of left parentheses P times Q and all that. But this is the type of work you need to show. And first of all, you have to talk about what kind of standard deviation you're looking at. The standard deviation of what? Is it the standard deviation of the sample? No! The sample does not have a standard deviation. The sample was so many males out of 550. It's just a sample proportion. That's the only statistic you get from that. So it's the standard deviation of all the possible sample means, which comes from that formula, PQ over N. And we actually have those. 0.517, 0.483 over N, which is 550. Now, we'll get that off the calculator in a second. The z-score comes from taking the the sample proportion minus the population proportion divided by the standard deviation of all the possible sample proportions. And so that's 0.569 minus 0.517 over whatever we get for that standard deviation up there. We can pop it in there too. And we make a picture, we come up with a p-value. And again, your picture should be consistent. So if you want to just talk about sample proportions, let's do that. We've got our central P is going to be 0.517. I don't really know where to put 0.569 now until I get a idea of how big the standard deviation is. So I'm not ready to finish my picture until I get some more numbers, and we're also looking for a p-value. And here's the other thing to watch out for too. The p-value is going to be in both directions, because we said it was a two-sided test. So we're going to look for the probability of having this result of 0.569 or something more extreme than that in either direction. So, you got your hands out, folks? What's the P naught? 0.517. That's from our null hypothesis. Successes? You have to go back to the original word of the problem. What does it say? Successes.
Is that NP?
No, it said there are 550 live births, and how many were male?
It's a G6.9.
Oh, see, so it gave you the percentage then, right?
Yeah.
So this is what you have to do then. That's the one inconvenience here. It's assuming that a lot of problems tell you the number of successes, and then you have to actually divide out your p-hat. This problem is actually giving you p-hat in advance, so we have to kind of work backwards to use the calculator. But I believe you can just say 0.569 times 550, right there. Did it like it? It didn't crunch it out yet, though. I think it will. 550 is the number, right?
It's a domain here. Yeah.
Okay, somebody on the side, we have to calculate that out separately.
It's 284.35.
284.3, so it's probably 284 then, right?
No, it's not. It's 3.
You can have a decimal in your.
Right, it's not going to let you put a decimal in number of successes.
We're multiplied by 0.569.
0.569 times 580.
Oh, 0.569.
So that's what you have to put in there, 3 to 13, okay? 313 for the number of successes. And then, what are you going to use for your alternative hypothesis? You're given a choice there. Proportion is not equal to P naught, proportion is less than P naught, proportion is greater than P naught. What do we want in this case? Number of successes is 313. So now I'm on the alternative hypothesis section of the one portion z-test on the T89. Which one are we picking? Not equal to. So you pick not equal to. And then results, you can either calculate or have it draw the picture. I think we just want to calculate. But if you want to, it will draw the picture as well and show you the areas. And you have to enter twice there. Okay, it's going. We got some key numbers off here now. We get a z-score of 2.44. Maybe see where you can get the z-score from. 2.44. So in red here is the stuff I got from the calculator. Also, you can get the standard deviation off of here too, I believe. Do you see it in there? Oh no. Oh well. But we get the p-value. 0.014, right? 0.0145, 1.45%. And a z-score of 2.44, that's more than 2 standard deviations above the mean. So we're way over here. So when I draw my picture, I'm going to show 2.44 in each direction. Here and here, because it's a two-tail test. Yes.
If we're doing it like that, wouldn't the normal curve have to be like 0 as the mean and then...
Right, but that's why I labeled this point p hat. If I were drawing a normal curve, like this, I'd label this z, and then this would be 0.
And then you could put the...
Right, and then there's your 2.4. Because the p-value in this case, the p-value is going to equal the probability of getting a z-score greater than 2.44 or a z-score less than negative 2.44 because this is a not equal to case. This is the two-sided alternative hypothesis. Yeah.
How do you know it's two-sided again?
From our alternative hypothesis, we said not equal to. Instead of strictly greater than, strictly less than.
Okay.
If we had done strictly greater than, I would have just stuck with this. Stuck with the right side of that curve. Okay? So, the only thing missing from what we should really show when we write this up on an AP is what is your value for the standard deviation. It also makes this picture a little better. So, I think we're done with the test. Let's go through the same test again and see what it does in terms of the picture. Okay? Test. So you also notice that it'll keep the same stuff in there too. Go back to F6. One proportion z-test. So the same numbers are still in there. But I'm going to change from calculate to draw. And it basically, I think, is going to show me the the standard normal curve. Oh dear. I didn't get it very good. Oh no, there it is. It's because I had something else in there. There's the standard normal curve. And it says the z-score and the probability again, and the p-value. And I think you can just make out the little tails it's filling in on both ends, if you have it dropped, okay?
How is there only one p-value when we're doing it a double-sided?
Oh, because you're taking the p-value. There's only one p-value because you have summed up these two areas.
Oh, it's the sum.
The p-value is the sum of those two probabilities on either side, okay? All right. Okay, so maybe you can get on the notes there. Does she have the standard deviation listed calculated out?
Yeah.
And that's what?
0.0213.
0.0213. So if you go about 0.02 here, you're up to 0.538 and then 0.558 think so. So, 0.5 deviation. There you go. Okay. Now, ready for the conclusions. State your conclusion. And now we have to carefully go through. There's two aspects to this conclusion. There's making the decision and then putting your decision in context. And make sure you do both. So first of all, are we going to reject or fail to reject? Reject. Why? It's significant? How do you know it's significant? It's less than 0.05. Okay. We reject the null hypothesis. We reject the null hypothesis because the p-value equal to 0.01. What was it? 0.014 is less than 0.05. The p-value is small.
Is that the number we're always going to use, 0.05?
No. This problem did not specify a significance level, and we're going to talk about that in a second in check 21 next. But if a significance level isn't stated, a reasonable significance level is either 0.01, 0.05, or 0.1. No, 0.05 is usually top, like 0.001. 0.005, okay. So usually 0.01 or 0.05, but nothing bigger than that. The p-value is small, and that leads us to rejecting the null hypothesis. So I've kind of stated it twice there, but I want you to get the idea that right now we just talk about it seems significant because it's small. Later on we'll talk about this specific. Okay. Now, that's only half the story, but you have to make that connection. You can't just start stating a conclusion without mentioning the p-value. All these four parts of a hypothesis test are connected. And in each, when you go to another section of your whole big proof, and we're in the conclusion section now, you have to go back to your number crunching and say, what's the key number you got out of that? The p-value. The probability that this experiment would happen, or something more extreme than it. So, there is sufficient evidence to show that, now, you can't just stop here and say P is not equal to 0.51. Say it in words. Use the context, and make sure you're using the right context. What is the word for P? That the population proportion of male births is not equal to, and what was it before, 0.5, what did they claim before? 0.517. There. What we have in here are the key things that we're going to be looking for in the AP. Have you made the connection to the previous step? Have you somehow told me about the p-value? And also mentioned and compared it to your significance level? Also, did you make a decision? Don't just discuss the p-value and never make a decision. You have to make a decision. You're going to reject the null hypothesis or fail to reject it. And if you reject it then we say there is sufficient evidence to show that the population proportion of male births is not equal to 0.517. Okay? Did Ms. Lance come to the same conclusion?
Yep.
Good. All right. So that's another example. Hello.
We didn't really answer the question though if it's a change.
Yeah, because it's not equal to the old.
So
it has changed.
So do you have to write the percentage of?
Don't start giving an estimate of how much you think it's changed.
No, can you just say or don't you have to say the percentage of males born has changed? Because that's the question, if it's changed or not. Yeah, that's what she is.
Well, I said it's not equal to what it was before. So it has changed. the P, has changed. Okay? All right. Now, something happened while we were writing. Okay, here we go. Works here. And let's look at the example again. What is all that stuff? Oh, it didn't cook to the right anything. That's okay. We just clear the screen. Oh, where's my little things disappeared? Why'd you take those away, people? Where's where's that little thing? Gotta call up the tools again. Why is there all that writing? Because I think somewhere in the middle of the process, the smartboard tools just shut down. There you go. See, now they're back. Okay?
We'll still on the screen.
Yeah,
That is a nice whale.
It's blue.
And here we're looking at the example again. Bingo. Okay.
I think you have to use the eraser flash.
Sure.
no, just double click.
Oh.
Who's a genius? Oh,
You can
God.
make it bigger.
Oh, you can do like where you circle all the way around it
Yeah,
and
and then
tap in
double
the
click.
middle.
Double click.
Oh, okay.
Okay, there's our answers. Okay. We reject the non-hypothesis, so we have evidence that the birth ratio of boys and girls has changed. Where do the actual birth ratio might be? Let's find a confidence interval now. See, now this is a different way to approach the problem. And that's to create a confidence interval. Right?
You missed a couple spots.
Yes. And see if the confidence interval contains our old proportion.
It's the black bar on there instead.
And can
And.
both those up.
Oh my gosh.
But no, the red one is left, up, below, missed it, below, up.
Below the M male and on the A male.
There, fine. People, can you read it?
Proportion and C interval.
Yep, no. Oh, I
You missed proportion.
It's too crooked.
Right in front of the O.
Proportion on the
Right
very
there,
bottom, right there.
The last line.
Fudge, you missed a
And also
spot.
your ass folder stuff.
Oh, wait, there's one more.
That could be misconstrued as
Oh,
factorial.
wait, male birth. The M.
Oh, yep, I
Oh,
see
yeah.
that.
I can't
even see it.
Percentage of male births. Let's
Between
find
C
a
and
confidence
interval.
interval for the percentage.
The nice thing about this is you won't be able to see any of my hand gestures. Okay? All right. Now,
Seriously, that's.
we already checked the assumptions and conditions. We're going to find a confidence interval for the percentage of male births based on what, though? Based on P hat. Right. As opposed to working off the old and seeing how far our thing was from the old standards, we're going to set a new standard. We're going to say, hey, we just did a test. Let's see what our confidence interval is for that. We've done the assumptions and conditions, and they're satisfied, so we can model the sampling distribution with a normal model and find one proportion Z interval. So let's practice doing this on the calculator as well. It's not going to be handy. Here it goes.
I think you have to use the eraser to click it.
Really? Let's see what happens here. Okay, here are the mechanics. We got 5 and whatever. Apparently this stuff isn't sliding along with something. Oh boy. Let's try this. Oh, that's usually not a good thing.
Why do you like slide it there when you just tap it?
Hmm?
Why do you just tap the center of the X? Why do you slide it to the X?
Flames, you know, for
It's where you release it, so it doesn't matter.
Oh, okay.
Just tap it. Okay, will the standard error have changed then? Yeah, because now standard error is square root of P hat Q hat all over N, square root of 0.569 times 0.31 all over 550. And so for a 95% confidence interval, you probably have this value memorized, right? 1.96. And the margin of error then is the z star times the standard error. So that's going to be 1.96 times the standard error, which we're going to get from up there, right? And so we're ready to do the confidence interval. Well, let's see what the TI-89 can whip up for us, okay? So, go to the same situation again. Let's go to catalog, or to apps, stats menu, stats list editor. And this time, you're going to go to intervals, F7. Did you find that, kids? F7, okay. And we want a 1 proportion Z interval, right? That's number 5. Is this on the next page of notes too? Now, our successes, notice it's kept the same successes. Mine still says 313, even though we're doing a different test. Isn't that handy? Kind of remember, thought, oh, you want the confidence interval as well, so let's just keep everything the same. So my 313 was still in there, and under N, it still has 550. And the confidence level, you can change anything you want. You want to stay with 95, right?
Wait, why is 313 the same if we're doing, when we do p hat times 5?
Wait, where did you click this one?
Yeah, but doesn't that work out to be 313?
No.
Oh, I am
That
so
was
sorry.
1.517.
Oh, okay. So sorry. Yes, you got to do the successes, the new X value. And what does that work out to be?
I'm in my stats list.
Wait, what do you want to know?
Wait, didn't we do this before?
Point-
You used 0.569 before, right? Yeah, it's
Was
313.
it? Oh, yeah, I thought we did
Yeah, see,
0.517.
we put that in as P naught.
Oh,
And then it asks for. So at least it's being consistent that way. That it's when it's asked for a number of successes, it's based off of the trial you did, as opposed to the status quo. So yeah, we're good with 313 and 550. Okay, here comes the interval. And it says the confidence interval is from 0.5277 up to 0.61053. Okay? And the p-hat was 0.569, yeah, we knew that. The margin of error ends up being 0.04138, so that's the plus or minus, right, on our interval there. And again, it still didn't give us the standard error, which is going to be a little different than our standard deviation curve. Right?
Oh, wait, what are we multiplying 1.95?
Exactly, that's why I'm waiting to get off the calculator here. Karen's got that number sitting in front of her somewhere. What's
0.0211.
0.0211, that's a little different than before, isn't it?
Wait, what? I don't like this. Oh, this is 550.
What?
Is there a
Which part?
550?
What aren't you getting out?
I don't get like why.
Okay.
And what is the
So Z equals
That is
1.56 and C is
0.615?
Okay.
Oh, 1.615.
And now it goes real quick for them.
Okay.
Oh, nice.
Okay. Now, that's not the you shouldn't stop there and just say that's the confidence interval. You should go through the whole description. We are 95% confident that the population percentage of male births is between 52.7%. Oh, it's on the next page, okay. So let's go to the next page. State your conclusion. Okay. I think there's a board, I think there's a clear white right here, isn't there? Doesn't it say, no, not that. Shoot, I remember seeing it before. Sorry. Let's just get a bigger eraser going this time. Okay.
There's writing on the board.
That's where we were. State your conclusion. Okay.
Did you just make the symbol of the?
That's right.
No, like you know that little circle that is showing when you're erasing.
Yes.
How it shows? Can you make that bigger?
Yes, that's what I tried before. I went over here and went to this. All right. And this is the bigger eraser now, isn't it? Okay. We'll get through these technical things. So, we are 95% confident that the population proportion of male births is between, and what were our two percentages there? 52.8% and 61.0%. Okay? That's stating a proper conclusion for a confidence interval. But now we're going to tie it into the actual test that we're asked to do. Right? And that was to say, has it changed? The null hypothesis of P equals 0.517 is not in the interval. So therefore, we conclude that the population proportion of male births has changed. And that's all we asked. We weren't asked to show that it has gotten bigger, although certainly we have evidence for that now. Our whole entire 95% confidence interval greater than the old proportion. So there's evidence for that. Okay? Okay, so now we're about a